Good afternoon, everybody. If you have any questions, we can do the discussion here in this live session. Okay, so there were some questions posted priorly. So one question was about assignment one, question 19. So it was, how is CPI directly proportional to clock frequency and related to that, right? So if we just seek a clarification, we look at the expression for the execution time. So execution time was the instruction count multiplied by the CPI multiplied by the clock period. So the TC is not the clock frequency, but it's the clock period. And if you reorder this using algebra, what is the CPI? So CPI turns out to be the execution time divided by the instruction count multiplied by the TC. So the clock period goes in the denominator when you are computing the CPI, and 1 over the clock period is the frequency. Hence, CPI is directly proportional to the clock frequency. Right. So that's why the answer was CPI is directly proportional to clock frequency, and it is directly proportional to the execution time. CPI is inversely proportional to the clock period, but directly proportional to the clock frequency. Right, so this was the answer to one of the queries. All right. The second query was that if one is working in the VLSI domain, how does the PCA course or the topics which we study specifically in this area, and what should be our focus in this for in terms of future technology? Right. So in this PCA course, we are looking at more pedagogical aspects, more theoretical and foundational aspects of how a parallel architecture should work. Definitely, there is a lot of scope of this for future technologies because we studied memories, we have studied the coherence, and if one is interested in cache coherence, you can work upon improving or coming up with more variants of the cache coherence protocols. During the lectures also, we've discussed that one particular, for example, NESI is a protocol, but it has many different variants and different companies implement different varieties of the same protocol, right? So you can always come up with more varieties of your own protocols if you wish to contribute in the cache coherence domain, if you wish to contribute in the memories domain. If you are from a devices background, definitely different type of scope is there for emerging memory technologies. But from an architecture perspective, how do you manage more memories? We looked at, or rather in future lectures, you will look at interconnection networks where several memory modules get connected. So how big should a memory module be associated with one particular computer component? And can it be too big, too small, right? So you need to understand or devise methods about the size and capacity of these modules which you will be connecting, right? So there is scope for memory architectures, and what else can I say? The research aspects are definitely there. Because when you go to multi-core systems, apart from parallel programming, which is a completely computer programming type of a domain, one can look at multi-core architectures from a data center or a cloud computing perspective. So when you are looking at cloud computing or data center type of architectures, you need to consider a concept of disaggregated memory. So memories are distributed across various cloud servers, and if you want to run an application which may possibly map to a memory module which is on another cloud server. Okay, so you can imagine the type of latency it is going to incur. So in this case, can I relocate the data from the different cloud server to my own server? Right. So these aspects will also need an understanding of the interconnect, how coherence works. So once we study the PCA course and you also have the background of basic computer organization and architecture, you can apply this knowledge to a variety of fields which are coming up. Okay, thank you. Now take up questions from the chat box. Okay, so one question is that what type of job profile will this course help in for ML engineers or data scientists, etc.? All right. Okay, so ML or data science, these are not hardware type of subjects. They require a completely different knowledge domain, but I can directly say how you can use hardware for ML. It may not directly answer your question, but what is related or what is the overlap between ML, data science, and hardware is what I would like to highlight here. Is all the ML and AI applications, they involve a lot of parallelism, right? So you need to do a lot of compute in parallel. And all this compute requires us, of course, to store it in the memory. So you need memory to store your operands, do the operations on an arithmetic logic unit, and then again store the operations back to the memory. When you have to delegate this big task, which is itself a big parallel computing application, how do you distribute the workload? That is a parallel computing problem, but you can, of course, visualize that you have multi-core systems or multiple processing elements, which are not full-fledged microprocessors. They could be small, tiny units like DSP cores or ALUs or something like this. Right? So you have small processing elements, and how do you distribute your workload to these processing elements? That is one type of knowledge or work which you will have to do as an engineer. Once you distribute this, how do you collate the results? So that's one aspect. So if you're interested in task distribution, this is the domain you can work in. If you're interested in design aspects, that is, you are very keen on doing hardware designs, then you can also come up with better compute units. If you are good in digital logic, you can come up with adders and multipliers which are tuned or reconfigurable to the current demands of the system. For example, the ML algorithms change, their type of precision they work upon change. So you can design units which adapt to the changes happening in the ML or AI domain. This overall memory management, designing these compute units could be one area which overlaps between the ML, data science, and parallel architecture. Thank you. Okay, next question is, I'm a VLSI student. How can this knowledge help in building a better system? And career path, can this open up? So if you are a VLSI student, you are definitely doing several courses related to design, devices, and architecture. So with a master's in VLSI, there is a lot of scope in several industries, and as well as higher education, academia also has options. If you have a good master's degree and a specialization in a particular topic. So if you do parallel architecture or advanced architecture courses, you will be able to design systems. And most of the industries, and especially the Make in India movement, which government has started, would require hardware designers. With knowledge of advanced architecture and parallel architecture, I'm sure you would become a good hardware designer, designing memories as well as processors. And if you have an inclination for computing or software, then you can also develop algorithms to use these parallel systems. So yes, MTech in VLSI with such basket of courses is very good, and there are opportunities, and there will be more opportunities in the semiconductor industry for the young engineers. Thank you. Okay, sorry for the glitch. My microphone was muted. So what I was saying is those who are registered for the course, I'm sure you're all following the lectures and doing the assignments. If you have any queries related to the assignments or any doubts, you can ask them now or put your queries in the discussion forum. Definitely, there are issues once in a while related to some questions, or there's an ambiguity. You can freely discuss it with us, and we will try to either clarify your doubts or rectify any errors at our end. So the modules which we have covered is an introduction to parallel computing and memory hierarchy. These are the two main things which you must have studied till now. And the memory hierarchy topic has been overall a review of the memory hierarchy. Definitely many things are there in the memory design which we did not cover. And the topic on virtual memory itself is a huge topic. We only gave you a flavor of how the page table in the TLB looks like. And we have not discussed the design management of page tables, which are much larger. How do you manage them in the main memory controller? How are layered page tables existing? And what are the implications of the main memory size, the disk capacity on the size of programs which you can execute? Yes, so there are many, many questions related to virtual memory which we haven't addressed because the objective was to give you an overview of the type of memories that exist so that we can move on to our course on PCA, because we are interested in studying the coherence, consistency, synchronization mechanisms. For this, basic understanding of memory is required. Definitely, you are most welcome to discuss with us. If you have answers or you have come across something nice, you can put them in the discussion forum as information to other co-learners as well. Okay, next question is that can I elaborate on how a verification engineer of hardware design should approach this course? Okay, so verification, if you are looking at the correctness of the hardware or correctness of protocol, so if you have expertise in verification, you can use this course as a case study for doing verification of these protocols. So that's also an interesting area to work upon, because we discussed the MESI protocol, and the MESI protocol works on the snooping based system. It also works on a directory based system. Directory based systems, when we study them in future, you will see that there are three different implementations of the same protocol. So protocol is the theoretical foundation of the theory. That's the protocol. That's why we call it a protocol. Whereas the implementations will be various, will be very different across the type of interconnect I'm using, and also depends on industry, because they want a protocol which suits to their existing processor design setup. Right. So if you are a verification engineer, you can look at these aspects about how do you verify a protocol, first thing, and then when this is deployed to a particular system, does it do the work it is supposed to do? So I would say that, yeah, these are the two avenues where you can concentrate on. Okay, next question is, can PCA help in system design interviews? Okay, a tricky question to answer, because I'm a pure academician and do not know what is the requirement or demands from the industry. But definitely, a PCA being a very advanced course, along with the coherence and memory management, it is going to develop a lot of fundamental understanding of the student in architecture as a domain in large, because the students who work in this domain as master students or research students, uh, when they start working, you would also need to implement ideas when you propose a change or some small addition to your coherence protocol, or you want to implement that with some different memory feature. So any ideas associated with the topic of parallel architecture, when you want to experiment, you will develop algorithms, methods, and implementations, and then try them out on different benchmarking software. So that, as I had highlighted in one of the lectures, there are many simulation tools, there are benchmark suites. So all your ideas which you come up with, you will have to implement them in the simulation software, do the benchmarking for them, and then analyze whether your ideas are well functioning or not, whether they're useful or not. Okay, so in this whole process, you will gain a lot of knowledge related to systems as a whole. And this has definitely helped all the students with whom I have interacted. And therefore, PCA would, I'm sure it will help you in the interviews. So regarding the various assignments which we are releasing every week, our effort has been that we cover maximum questions possible to cover the complete 2 to 3 hours lecture which we deliver during that week. And the questions should make you go back and see, revise the lecture and answer. And therefore, at times, the question would need more relooking at and more understanding before you can attempt it. So they may not look very straightforward that, yes, I know this definition and that's the answer. So at times, you will also have to think before you answer. There could be some choices in the question which are ambiguous or which also look correct. But in such cases, I would encourage or give a disclaimer that those choices, the correct answer normally depends on what I have said in the lecture and not always, because there are many interpretations of a particular idea and different books say go to different levels of depth related to a topic. Okay, so if I have explained a topic in a particular way and I've said that this is the way a particular thing is working, definitely there are other implementation aspects available. But when you attempt the assignment questions, I would encourage that you refer to the lecture or keep lecture as a reference before you attempt the questions. And I'm sure you are all also filling the feedback forms because till this week it was more of a recap. So we did an intro to parallel architecture, which was more motivational and an overview type of a topic. Then we looked at memory hierarchy, which you all have been studying since your second year undergrads. But now on, we will start with the coherence and coherence protocols are if you understand, they're very easy. If you don't, then you will think that, oh, I am not following the course. So I have tried to explain them as slowly and as detailed with associated examples and explanations. So I'm sure you will enjoy learning it. But if you do not follow a particular concept, I would say that you go back and revise it, because the course builds on the previous lecture. So if you do not understand a particular lecture, it will be difficult for you to link the things which will come up in future. Right? So keep up to date. Make sure your concepts of a particular lecture are clear before you move on to other lectures. If you have any constructive feedback related to the content, the assignments, you are free to put in the discussion forum and also in the feedback forms. There's a question in the chat box which is slightly unclear to me. If you can elaborate a little on that leaf and non-leaf page table entry. Could not understand the question. Okay, the next question is, does the implementation of parallel architecture depend on the ISA being used? Okay. See, you definitely need some support from the processor. But as we will look at in certain modules in the future lectures of this course, I have demonstrated that you can take off-the-shelf processors and then combine them to construct a parallel computing system. And why is this possible? Because the processors, they come with their own ISAs. I can definitely have heterogeneous processors working on different ISAs. But when I want to combine them, I need extra support. So which I do not expect that the processor designer or the processor industry should provide it to me. You could design a separate controller module, which is capable of implementing your coherence and consistency setup, where that module enables the connection of these different processors over a bus-based system or a scalable interconnect, and your coherence mechanisms will be implemented within that new controller which you're going to design. Okay, so there, as a PCA engineer, even if you do not know the processor ISA, you can develop parallel systems by understanding coherence and establishing setup such that you can connect different modules to each other. So if you have 4 processors, you can say I will have a new bus implemented, and whenever the processor's accesses go up to the last level cache, these cache level accesses, before they reach the memory, you as your controller should also be able to look at them and take appropriate actions. So the systems which you will design as a plug-in devices kind of thing will sit between the cache and the main memory. So it will be able to interact with the main memory, your last level cache, the interconnect, and this of all the processors which you want to connect. Yes, it is definitely possible. Okay, next question is the logic in which the virtual memory concepts work. According to the same logic, does the VIPT, that is virtually indexed physically tagged cache system, work? Well, yes and no, because it does use virtual memory, but virtual memory is a concept which gives you an illusion of lots of memory being available. And it also helps the memory management unit to relocate your pages in the main memory. Whenever there's a context switch, you have a set of pages allocated to your process. And next time when you move out of the system and then you're brought in again, the assigned physical locations would be different for your process, right? So if you have control statements in your program or your data references are very hard coded, you would not know where to jump if you have go to some location and that location belongs to an address, physical address. And next time when you reload the process back into the main memory, suppose it gets reloaded to a new location. So your go-to statement will no longer be valid if it is based on a physical address. Hence, all the processes work on virtual addresses, and these virtual addresses are mapped to physical through the processes which we have studied. Okay, so that and other things which we studied in the lecture belong to the virtual memory concept. The other one which you have asked, VIPT, virtually indexed, physically tagged. So that is a type of a cache, and mostly it is at the lower levels, not closer to the processor. Because when the processor issues an address, it is virtual address. Okay, it's not a physical address because what I said a minute ago is every process is going to use locations as a virtual in the virtual domain and not the physical addresses. So when I have a go to statement, I am going to say go to line number 5 or address number 5. It doesn't matter that this address 5 is located at which location in the main memory, because the first time you started, your address 5 could be present in location 200 of the main memory. Next time it may be at location 5000. Okay, so your correctness and working of the program should not depend on where your program gets loaded in the RAM. Hence, all the addresses, all the processes use only virtual addresses. So when the processor issues an address, which is a virtual address, and you come to the cache to see whether it is a hit or a miss. So what's going to happen? Your address is virtual. Your cache is going to do an index That is, it is going to go to the particular set, and once it reaches that set, it has to do a tag compare. Now this tag is, what is it? It is nothing but the prefix, that is the initial portion of your virtual address. So if your virtual address is some string, you are going to match the upper half of the string with the tag. So your tag is also virtual because you have no time to translate the virtual address which is coming from the processor to a physical address, because you will need to go through a translation unit. The virtual address comes, you translate it through the page table, then you get the physical address, and then if you construct that physical address and then look up into the cache, you can imagine the amount of latency. Okay. Therefore, these caches which are closest to the processor, that is the L0 and the L1 caches, they are virtually indexed and mostly virtually tagged, because I want to do a quick comparison. All right, but as we go further in the memory hierarchy, suppose I go to the L2, L3, so-called lower level caches, then I can afford to do a tag comparison using the physical address. Right, so mostly we will take the virtual address and we will index the cache using the virtual address. But the tag stored inside the cache will be the tag belonging to the corresponding physical address of that particular location. So I come with a virtual address, index it using the virtual address, and I want to do the tag comparison with the physical address. So in this process, at some point, I need to translate the virtual address to the physical address. So I can have this time available only when I am away from the processor. Okay, so most of the cache hits will be handled by the first level caches. So higher level caches will do your cache hits. Whenever there is a cache miss, you will go to the next level. But when there is a miss in the higher level cache, you are going to schedule the processor on other instructions, either using instruction level parallelism or out of order execution or hyper-threading, something so that the processor remains busy. So my address which I'm accessing is not there in the L1 cache, which was virtually indexed, virtually tagged. So I will schedule the processor to do something else, and this cache miss will now go to the lower level. Now, when I go to the lower level, we have more time because we haven't stalled the processor. Processor is already computing. So I have more time to go to the next level and bring the data. So when I go there, I have the time to translate my virtual address to a physical address. And therefore, I can index the cache using my virtual index, that is virtual address, but I can do a tag comparison using physical addresses. So that is the concept of VIPT. Okay, so they are not directly related, but definitely not unrelated. Thank you. Okay, next question is, parallel architecture can result in more hardware in a fixed area. So how can we manage the power consumption? Well, parallel architecture is definitely going to give you a lot of processing elements, but it is up to the designer about how dense they want to pack these processing elements. Do they want to pack it in a close fit network? Because when you are concerned about power consumption, so energy dissipation, or you want to highlight about energy density, right? So if I have lots of compute units in a smaller area, what is going to happen? I'm going to generate a lot of heat, and this heat or the temperature has to be dissipated to the environment so that my chip can be cooled quickly, right? So you need better cooling systems and associated infrastructure if you have lots of compute units packed together. For example, your GPUs, they have thousands of small cores or small ALUs packed. So the power dissipation or the energy and the heat dissipation is very high in these systems. Okay, so yes, data parallel architectures do dissipate a lot of heat. But if you are concerned about having systems where they are not they are not in physical proximity, so then the power density is not an issue. But then it would lead to your communication latency. Okay, your systems are far off, so they don't heat up a particular area, but your communication would then take up more latency and power. Right? So yes, power consumption is high because the more you compute you want to do, the more power you're going to consume. So the applications and the softwares and all the environments related to data science, ML, AI, they are doing a lot of compute, and all this compute is going to happen on parallel systems. Parallel systems, if they are in close proximity, you get heat density. If they are far off, communication. But overall, yes, power consumption does increase when you do such high level or high density computes. There are avenues of saving on these power, which could be taken up as research areas by some students. That is, how do I optimally schedule an application on a system so that there is less communication which is happening, so that my memory accesses are belonging to the same module where the process is scheduled. So this way you can save power related to communication. You can save power related to the compute time. For example, you want to do a small arithmetic, so why employ a big adder or a big size multiplier if you can do it with a small size? That is, if you can do a 4-bit multiplier, why do you want to employ an 8-bit or a 16-bit multiplier? So this way, using optimal arithmetic unit and using better process scheduling and process mapping methods, one can address the power and energy consumption related aspects. Thank you so much for your comment. The question related to leaf and non-leaf in page table entry, it's not clear to me. If you can elaborate, I can take up that question. Any doubts? Normally, we try to clear your queries on the discussion forum within one day, but at times it takes a couple of days, depending on, because we also have weekly schedules of putting the assignments, the videos, so it may get delayed at times. So please bear with us. Any changes related to the assignment answers, in case one question had a wrong or an ambiguous answer, if we encounter such things, we try to rectify them. And the rectification takes some time because it is not done at our end. We have to submit it to the system, and it is handled subsequently. So please bear with the delay, because once you have put a query or doubt to us, and if we have said that we will look into it, definitely it will happen, but it may not happen immediately. But it is in our task list, and it will be definitely done. Next question is that one student does a BTech ECE background, and does he need to know about computer architecture and operating system to get better understanding of this subject? It would ideally help if you have the background, but I do not expect that, because in the prerequisites also I had said that basic understanding of undergrad level architecture course is sufficient, because you need to know how a processor functions. That is, it works, it fetches an instruction from the memory, it does a compute, and then it writes the answer back to the memory. Depending on the type of processor, the ISAs are different. It could be a CISC processor, a RISC processor, various implementations, various size of pipelines and all that. So that is the processor design domain, which is not a prerequisite to understand this. The basic understanding of what a processor does is sufficient to understand PCA, because we do not go into the design of the processor in the parallel architecture course. What we are going to look at, if there is an application, so any graduate in CS or ECE, we all understand software, right? So we do a first year level course on C programming. Subsequently, we'll also do courses on digital design. So once you've done a C programming course, you know what a program looks like. You have done array manipulations. You have written programs where you work upon many data items. During the course, also, I have illustrated that if you write such a program, you can divide the program into small pieces. So that level of programming understanding, if you're following, you will be able to visualize the application of parallel architecture. Okay, I have a big program written in C. I have chopped it into small pieces, and these will run in parallel on some system. Now, running the program in parallel means executing the instructions, which is done by the processor. But to execute these instructions, they have to be brought from the memory. To operate upon the data, we do changes to the data, which also will affect the memory. So when I am changing a data item, am I permitted to change the data item right away? Because maybe some other piece of my code may be using this data in parallel. Okay, so that the processor has got no idea. Hence, I say processor level understanding, even if you don't know, it is all right. You only need to understand that if you are operating on data item A and there are two parts of your program which are going to change this variable A, then they need to coordinate with each other, because otherwise the order in which they will change the data item is not known. And if it is not known, you cannot predict a correct outcome of your program. So today you run the program, you get an answer, some answer, tomorrow some other answer will come. So the reliability and correctness of your program will not be guaranteed if these shared variables, the variables which are common to multiple threads of your program, are not handled properly. So this level of programming understanding is expected, and I have also explained it during the lectures. If you're familiar with C programming, I'm sure this should be okay for you. Okay, so after that, the question of operating systems. See, again, OS is a big enough course, like virtual memory is a big enough concept, and everything is a subject in itself, I would say, because as you specialize in CSE, you would understand that each subject which you study in undergrad has a big research impact, and a lot of material is there on every subject. So I will say that yes, operating system is a big subject in itself, but I do not expect you to know operating system, because we are not using that as when we study PCA. Okay, so OS covers virtual memory. Even I have given you a flavor of what virtual memory looks like. A better and deeper understanding of the management of bigger, smaller memories, virtual memory, different disk sizes. All this is done in the course of operating system, but we are not going to touch those aspects. Okay, so what you need to know, that there is an operating system which will help me to communicate between systems. Because when I say you send a message, if you look at, I hope you've covered that lecture where we looked at the layers of application. You have the application layer, then the system software, OS is there, compiler, libraries, finally comes the physical hardware, right? So in this hierarchy, operating system is there. It is going to help the programmer's messages to finally go onto the network. So this is the role of OS. If you are sure, if you are comfortable or you understand the role of operating system, that should be sufficient, because it is treated as a module which helps me to communicate across layers. That is all the understanding I expect to understand PCA. Beyond that, not much. Okay, next question is, what is the current research trend of parallel architecture in the context of LLM and AI? Okay. Yeah, well, so similar answer to a previous question, that LLM and AI are application domains which are, they have their own field of doing their respective tasks. But these models or these applications, they run finally on the hardware, and the hardware they require is mostly parallel. If you are working in AI ML domain, you know that any inference or training task which you do, mostly it is done on GPUs, which are data parallel architectures. Okay, there is not much sharing in data parallel architectures, so it's all right. But in case there is sharing, then you need the understanding of PCA. So to highlight the overlap, I would say that PCA would give you an understanding about how do you place the processing elements, how do you assign workloads, how do you make sure that the data which you're operating upon is as close to the processing element as possible. Because in most of these ML workloads, I might not use a full-fledged processor. I might have a tiny ASIC or an FPGA which is doing this implementation, or an accelerator which is operating upon the data. Right, so all these accelerators also have several arithmetic units working in parallel. So, of course, many design aspects are there to this. We need not go into the depth of them, but overall, a lot of compute units are available. They're working on independent, most of the time working on independent data items in case of ML workloads, but in case there is sharing, you would need coherence. So overall understanding of PCA will help you to see the challenges associated with it, and you will get a feel of how can you design better systems for these AI ML workloads. How do these accelerators work? Can I have 100 processing elements to do my task, or should I have 1,000 processing elements? So the mindset of parallel computing in general, I'm not talking of architecture, but the parallel computing mindset will make you think about how to do work assignment so that you can do the task much faster. You will also develop understanding of that when you are executing your application, it should run on the compute units most of the time. That is the utilization aspect. In PCA or any architecture course, you think that, yes, the processor should not remain idle. When I give a task, the processor should always be busy. Even if there is a cache miss, I do other tasks during that cache miss time and I still utilize it. Even if there is a pipeline stall, I want to do something more. So we are very greedy in keeping the processor busy. So this mindset develops as an engineer. And when you have a parallel accelerator with lots of compute unit and you have an MLAI workload, your mindset will be that how do I keep most of them busy? Because if everybody is busy, I will get a faster outcome. Right. So if 1,000 units are working at the same time, it will give me a faster answer compared to 100 units working in a sequential manner. So that would be an overlap, we can say, but directly there is no overlap because all these workloads work on parallel architecture. That's the baseline overlap. Next question is, what are the research avenue areas opened in PCA? We discussed this. Maybe I'll try to answer it once more. Parallel architecture, you're going to look at the cache coherence mainly, but you will get a feel of how to do memory management, how to do task allocation. The coherence protocols itself is an avenue to work upon if you want to suggest modifications or some optimizations to a particular protocol. You could work on that. As you would see that various industries are having their own versions of implementation for a given protocol. So they do those changes to suit their systems, right? So depending on the other system constraints, do I want some changes to the protocol for managing memories? For example, um, you you have a cache and the main memory, and you know where the data is stored. But suppose you add another module like a scratch pad or somewhere where you are making an additional copy of your data uh, for some reason, right? So there are multiple reasons one would want to do this. And when I have locally within one processing module, I have two copies of the data. For example, most of these caches, when they evict the data, it goes to the next level cache or the next level main memory in a write back cache. Suppose you want these evicted blocks to be readily available in future because you think these blocks will be again used immediately. So you don't want them to be written back to the main memory, or even if you write them back to the main memory, you still want to maintain a copy of that on your chip. Okay, so that you can save on the latency next time it is accessed. So such blocks can be kept in auxiliary storages, scratchpad memories, victim caches somewhere. So the name is not important. You might want to maintain these copies. So when you have this, you already have your own two copies in the system, whereas cache coherence is overall managing copies across different systems. So how does the protocol know this? So therefore, you will need some changes to the protocol to make sure that whenever a block is invalidated or accessed, apart from your cached copy, you would also want the system to look up in your auxiliary storage as well. So these changes need to be done to the coherence controllers to manage the correctness. So you can think about that. So PCA understanding would help you to do this. And yes. So in cases of cloud computing or data center based computing, each processor definitely has a cache, but it is working on lots of data. Hence, the memory are really large, huge. These huge memories are not physically adjacent to the processing nodes. So they are far off. Maybe they are on another cloud server. Okay, so how do you manage the memories which are so far off? We are not going to study this topic in the PCA, but the understanding will help you explore these areas, that how to access remote memories, what is the concept of a remote memory, and the associated costs or matrix which you need to take care of. That is the communication cost, the latency. If it's a cloud system, then you need to pay per use of that particular device. Hence, if your compute as well as a memory, if it is localized within one cloud server, it is more beneficial. So you will develop these understandings, and these are the avenues where one can contribute as research. I couldn't understand the question. If possible, kindly record a lecture at the end of the course modules. So can you please elaborate? What do you expect from this question? Yeah, thanks. I couldn't read it properly in the YouTube chat. So record a lecture on it at the end of the course modules. Okay. Yeah, so thanks for the suggestion. Maybe towards the end or when we complete the course, we can have uh, a summarizing lecture of future trends to PCA. So after the subject is over, maybe we can record it in due course and make it available at the end of the PCA subject. Or during the live sessions, we'll keep on talking. So I'll keep giving inputs and make notes about what you want. In the end, we can do this. Thank you for the suggestion. Okay. So if there are no more questions, we can close this live session. Thank you for those who could join, and thank you for keeping your questions alive in the discussion forum. So that shows that yes, you are following the lectures, you're doing the assignments, and you're eager to learn. So keep your curiosity alive and learn PCA. It is a new subject. As you study, you will avenues will come up, more ideas will come to you on your own. Only thing as a instructor, our job is to kindle that curiosity within you. And I hope we'll succeed in this. Thank you so much. See you again in the next month's live session. Thank you. Bye-bye.